Piecewise functions often represent real life better than just normal functions. And an example, look at the housing market. The housing market steadily increased, and then there was a big boom with the housing market. That might be an exponential. And then it finally busted, which might be represented more by a quadratic, because then it started to rise again. So each part of this, that's a linear, that's an exponential, that's a quadratic, and now maybe we're back to linear, but the whole point is they have a bunch of different parts to them. That's what piecewise functions are. So look at our first function. This says graph f of x for 2x plus 1 for this domain if x is between negative 3 and 1. So I can make a table, and on my table, actually that one's already made for us right here, I can just plug in my two values. So negative 3 and 1 are the two values I'm going to plug in. So if I plug in negative 3 for x, 2 times negative 3 gives me negative 6. Negative 6 plus 1 is negative 5. And then do the same thing for the 1. 2 times 1 is 2, plus 1 is 3. So now I have two ordered pairs that I can graph. And I'm checking here, I have an equal to sign there. So that means my negative 3 is going to be a closed dot. And then my 1 does not have an equal to symbol, so that one's going to be open. So negative 3, negative 5, that means I go left 3, down 5, and that is a closed dot right there. 1, 3, go right 1, up 3. And we have an open dot. And I know this is a linear function. It's in slope-intercept form. So I'm just going to connect that with a straight line. Alright, we've completed one part of our piecewise function, but now we have another piece. So the other piece is x minus 2. That's only true if x is between 1 and 4. So again, I'm going to make my table. I'm going to plug in my two values for x, 1 and 4. That's my minimum and my maximum. And the first one's going to be closed, and the second one's going to be closed. And again, the reason those dots are closed is because we have the equal to symbol. So plug in 1 for x, 1 minus 2 is negative 1. Plug in 4 for x, 4 minus 2 is 2. And now I just graph those two, and I know it's linear. Actually, these are both linear. So I go 1, negative 1, closed dot, 4, 2, closed dot, and I know it's linear, so I'm just going to connect them in a straight line. Alright, I'm going to get some graph paper out and do one more example. This one has a quadratic in it, and it's going to be made up of one that does not have between functions. Like this is where x was between two values, so it's a little bit different. So for this one, let's do f of x equals 2 if negative 4 is less than x is less than or equal to negative 1. And then f of x is going to equal x squared minus 1 under the following domain. If 0 is less than or equal to x, is less than or equal to 3. And one more. F of x can equal negative 1/2 x if x is greater than 3. Alright, so let's do our table. And for our table, for the 2, the first function, f of x equals 2, that's just like y equals 2. So it's always going to be up 2. But only for this domain, -4 and -1. So this table is pretty easy. So when y is 2, it's going to be x is -4. Again, I got that number from the domain here. Those are my two x values, -4 and -1. When x is 4, y is 2. -4 when y is 2. When x is -1, y is 2. In fact, y is always 2 under that domain. And the first one's going to be open, the -4. The next one is closed because of the equal sign. So open, closed. And I'll just graph those. So -4, 2, go left 4, up 2, open dot. And -1, 2, closed dot. And then just connect them. And it's a straight line, it's linear. Alright, our second table, our x squared minus 1, we have a quadratic. And on this quadratic, we're going to plug in 0 and 3, because that's what x can be between, 0 and 3. They're both closed because of the equal sign. And if I plug in 0, 0 squared minus 1 is -1. 3 squared minus 1 is 8, because it's 9 minus 1, which is 8. So then I go 0, -1, that would be down 1. Whoops, it's a closed dot. And then 3, 8. Now I know it's a quadratic, so I can't just connect these. I'm going to do a couple other points, test points. So what if I would plug in, for instance, 1? That's another, because see, this is where the quadratic's going to go. I just don't know exactly what it looks like until I plug in some more test points. So 1, I'll plug in. 1 squared minus 1 is 0. So 1 zeros on there. And then I'll plug in 2, and then I should be good. So 2 squared is 4, 4 minus 1 is 3, so 2 comma 3. And now I just connect these points. And it looks like it's basically almost half of a quadratic. Alright, my last table is the -1/2 x. And it's for, let's see, this one's different. It says x is greater than 3. So 3 is going to be one of my points that I use. And that's going to be open. But this says x is greater than 3. So I know that it's going to go forever. The domain is from 3 to infinity. So I can pick any number greater than 3 for that other point. So maybe I'll choose 6. And that one, of course, is going to be closed, and it has an arrow. Again, think, why does it have an arrow? My domain here is x is greater than 3. It's from 3 all the way to infinity. So it's going from 3 all the way in the 6th direction forever. So plug in 3, And negative 1/2 times 3 gives us negative 1.5. And then negative 1/2 times 6 is negative 3. So I'll graph those 2 points. So 3, negative 1.5. That one's open. And then 6, negative 3. I just realized I was off by a point. That's better. And then 6, negative 3, 4, 5, 6. And this is a linear graph, so it goes forever in that direction. So I'm going to put an arrow there to indicate that. Alright, we've done some piecewise functions. I believe we have not done them, we have performed them, said the wise owl.